This conference will now be recorded.
So very good morning, students. Today we'll be discussing, as you know, we had already started discussing electric field and potential due to an electric dipole. Yesterday we had somewhat discussed about electric potential created by a dipole. Today we'll see the field, how the field varies with distances, etc. And today we'll take up one more thing, that is equilibrium of a dipole. Equilibrium of a dipole, and then we'll start a little bit about Gauss's law. Okay, so let us start our discussions for today. So this is somewhat recapitulation. Electric potential due to a dipole. If you remember, we had found out electric potential due to a dipole at this point P is P cos theta by 4 pi epsilon naught r square. So this is the electric potential due to a dipole, and you can see here the electric dipole varies as potential due to electric dipole varies as 1 by r square. And in case of point charge, so this is for dipole. In case of point charge, how potential varies? It varies as 1 by r. That is what we had discussed yesterday. So if you have been given a plot like this, so this is potential, this is distance. So in case of point charge, it will be like this, and electric potential due to a dipole, it actually dies out very fast. So this is 1 by r square variation, and this is 1 by r variation. So this is what we had discussed yesterday's class. Today we will be finding out electric field due to an electric dipole. Okay, so there are, see, if I have a dipole, I'm just drawing it here. Suppose this is positive charge and this is negative charge. So dipole moment has a direction negative to positive, as you know. From negative to positive, that is the direction of this dipole moment P. Okay, so if I want to calculate electric field due to this dipole, I have two scopes. One, at any point on the axis of the dipole, this is called axis of the dipole. If I extend the line joining the charges on either side, then I get the axis of the dipole. So I can take a point like this to calculate electric field due to the dipole. So this is called electric field due to the dipole on its axis. Okay, electric field on its axis, dipole axis. Or otherwise, I can have a perpendicular bisector plane like this. So this is bisecting the line joining the dipole. So I can have a perpendicular bisector plane like this, and I can calculate electric field at any point on this perpendicular bisector plane. So this is called equatorial plane. Okay, this is called equatorial plane. And when we'll be sometime giving a name, electric field due to dipole. Okay, electric field at any equatorial point due to a dipole, and electric field on its axis due to dipole. So like that we'll be doing. So here in this figure, as you see here, so let me erase this part, and I have this figure already. So electric field due to dipole, and where we are calculating this electric field, that is at any point on the axis. Okay, electric field due to a dipole. Let me write electric field at any point on the axis of the dipole. Okay, at any point, here the point is P, on the axis of the dipole, axis of the dipole. So this is one point. Okay, so yes, so this is one problem. If you have been asked to calculate the electric field due to a dipole, and electric field where you have to calculate on the axis of the dipole. So in that case, you look here, if I just consider this point P, P just on the left hand side of this positive charge. This is positive charge, this is negative charge, and see, I am taking the separation between the charges to be 2a. So middle point, see midpoint, this distance will be a. Similarly, this distance also will be a. Okay, so now what I can do, I have to calculate, see this point, let us say this point from the middle point of this dipole, this point P is at r distance away. So if this P point is r distance away from the middle point, then I can actually find out the distance of this point P from positive charge and negative charge. Now look, whenever we are calculating electric field, we will be actually calculating due to, see, the total electric field will be the sum, vector sum of the electric field at P due to positive charge Q and electric field at P due to minus this charge, negative charge. So for both the charges, we have to calculate the electric field. So better to give the notation here, plus and electric field due to negative charge. Negative charge. Okay. All right. So see, if I want to calculate, see this is points now. While calculating this electric field due to positive charge and electric field due to negative charges. So here, so this dipole is actually point dipole, in the sense the dipole, the charges of the dipole has very negligible dimension. So these are actually point charges. So when I calculate this, I'll be using my concept of electric field produced by a point dipole. Okay, sorry, point charge. So in this case, this EP, sorry, E plus, say, electric field due to the positive charge. So this one. So this distance, so I have to find out. So Q by 4 pi epsilon naught, and the distance will be this one square. So this much is r minus a whole square. Similarly, if you see this charge, so this a plus a will be added. So a, sorry, E 4 pi epsilon 0 r plus a whole square. Okay, so these are two electric fields. So now you need to do little bit of simplification, as you know. So I have to see here actually negative charge, this is positive charge. So ultimately the vector sum of this will be, see, now if I add these two, see this is negative, so we'll be having Q by 4 pi epsilon naught. This much we can keep in our hand. Now this is r minus a whole square. This is minus r plus a whole square. Okay, so we have to actually find out electric field by combining the vector sum of like or getting the vector sum of the electric field here, that is the electric field due to positive charge and negative charge. Okay, so if we go with this, then see electric field ultimately see what we get here. I'll just go to this point. I'm taking the magnitude anyway, q by 4 pi epsilon naught. This is actually q by 4 pi epsilon naught into, so this will give you 2a here with a minus sign obviously. Sorry, this will be plus sign only, 2a with a plus sign, and in the denominator there will be r square minus x square whole square. So this is, see, 2aq, that is actually p divided by 4 pi epsilon naught. This is r square minus a square. Okay, now if this r square is, look this, r is the position, so r square, if r is much greater than a dimension or the separation between the charges, so if r is much greater than a, in that case, you just take this common, p by 4 pi epsilon naught. Okay, so r to the power 4 1 minus a square by r square. So in this case, look, this term could be actually neglected. Okay, I think there will be another term which I am just missing. I'm sorry, actually this will be, see, this will be r plus a whole square minus r minus, so a plus b whole square minus a minus b whole square, so this will be actually 4ar. Okay, 4ar, so this will be 2p, so this will be 2p, so 2p by this. So 2p by this one. Now there is one r also. So in this case, so this part if we neglect, then we get for so 2, 2pr by 4 pi epsilon naught r to the power 4 here, then the other part is neglected, so this is r to the power 3. Four pi epsilon naught r cube. So we can see that electric field due to electric field due to so what we get here, we get electric field due on its axis, we get as 2p by 4 pi epsilon naught r cube. So this is what is the electric field due to a dipole, and where this electric field is looking like this at any axial point. And see, this electric field could be written in terms of vector. Okay, so in terms of vector, we can just make this p and this as r direction. So then in that case, r cube will be r to the power 4. Okay, so now we'll see if the electric field is calculated at any point. So electric field due to a point charge at any point on the equatorial plane. I have already discussed what is equatorial plane. Now we'll directly go to the calculation. So in this, you can see here that this line PP, this line is actually perpendicular to bisector line, okay, on the plane, and it has constant potential hence. So if I start calculating the electric field, so how do you do that? As I know, so look, this is the point, and this is kind of square, sorry, equatorial plane. So this is, so this also A. So that is fine. So in this case also, what you need to do, you have to find out the electric electric field due to positive charge, electric field due to negative charge. So we have to first calculate the electric field between, electric field due to the dipole on the perpendicular perpendicular bisector. So I'll just write down So this is 1 by 4 pi epsilon naught. So sorry, this is A. So here this is also 4 pi epsilon naught. Sorry, this is actually electric potential due to, sorry, electric field due to negative charge. Okay. So the direction of electric field you can see from here. Suppose this due to this, so this will be in this direction, and this direction, this will be this direction. Okay. So you know we can have, if this theta, this is theta, then we can have excuse me. So we can have a component of electric field of this one along this direction and this direction. Similarly, for this also we'll have component along this direction and also this direction. These two vertical component will cancel each other. Only thing is that there will be horizontal component along the direction perpendicular to the bisector. In fact, so we can actually, I'll just write the final answer for this. So finally, what we are going to get? So finally, actually, we will get electric field electric field so this is net electric field minus EP okay. So P for positive, N for negative. So if we take this, actually there will be cos theta here. Why negative? Because this is just opposite to the direction of the dipole. Okay. So this value will be, obviously there will be an approximation. So at this condition, electric field so this is Okay, so this was equatorial plane. In case of equatorial plane, at this condition. Now there is a time to compare. Actually, see, I have few values. Two p by 4 pi epsilon naught r cube. That is due to axial point. Axial point. Equatorial plane electric field equatorial plane will be minus p by this is also r cube. Both are r cube. Now so we have got the electric field and both the cases at this condition. This is equatorial plane. Equatorial plane. Now we'll move on to the next topic, that is equilibrium of a dipole. So when a dipole is placed in a uniform electric field, as you know, it will not experience any force. It will only experience a turning effect or torque. So equilibrium of a dipole, how it is? See, if this electric field direction is this is the dipole direction, negative to positive. So these are actually similar direction, or they have 0-degree angle between them. Okay, this dipole and electric field has this angle. Now, when this angle is theta between them, that means what is the potential energy of theta? So this we had got P cos theta. Okay, minus P cos theta. This is what we had got, the electric potential dipole due to dipole. Now we have seen that if the electric field and dipole are in the same direction, then there will be a torque. There will be a torque, as you see here. There will be a torque acting on the object. Okay, and that torque will try to rotate this charge system, mass and charge system. So this is restoring force. This actually acts as restoring force. That means it is bringing towards its equilibrium position. Now when theta is equal to 0, theta is equal to 0 means this is P, this is G. Both are in the same direction. Okay, so in that case, you know, the angle between them is theta is equal to 0 degree, as you see here. and at 0 degree and 180 degree the dipole will not have any torque acting on it, neither it will experience any force. So at, see, the minimum value of this is minimum U occurs at, so this is, see, minimum value will be only minus PE, because after this theta has no value at theta is equal to 0. Okay, so when it is actually theta is equal to 0 configuration. When so what is the maximum value and when it occurs, when, see, this minus is there, so when cos theta is equal to pi, or that means PEI. Maximum potential energy is two of this. Okay, so this is, okay, so this is actually, this, see, this is also at this position when the dipole are at parallel, like parallel, they are parallel actually. In that case also I had to supply these values. Okay, so theta is equal to 0 and theta is equal to 180 degree. At these two, the torque will be actually in equilibrium. Torque will be in equilibrium, but in which case the dipole uh, have the, what to say, so just a minute, what we are just trying to see is, like, tell is that when you have dipole like this and electric field is like this, so when parallel, that case is there, and when the electric field is this and this is dipole moment is in the opposite direction, then what is the potential will be minimum here, maximum here. Okay, when anti-parallel, then potential energy will be maximum. Okay, so what will be the stable equilibrium condition in this case? Stable equilibrium condition is how much? So stable equilibrium position will be only when theta is equal to 0, because that time it will be maximum. Okay, so theta is equal to 0 condition is the stable equilibrium for dipole, and not this one. Okay, so that's why when a dipole makes an angle 0 degree, or that means that is they are parallel or anti-parallel. So in case of parallel, direction of parallel in the direction and direction of electric field and direction of dipole, that is what I am terming as parallel, anti-parallel, etc. So stable equilibrium position will be theta is equal to 0 position. Okay, that is stable equilibrium position for dipole. Now we'll be learning a little bit about Gauss's law. So what is Gauss's law? Actually, we have seen in the previous few sections how to calculate electric field due to different charge distribution. Okay, line, then space, etc. So Gauss's law is actually a tool which simplifies the calculation, field calculation. Okay, simplifies the field calculation. But when the calculation of the electric field will be uh, so if there is actually any symmetry in the distribution of charge, then only we'll get this advantage of Gauss's law. Like using Gauss's law, you can find out electric field at any so if I have certain geometry like sphere, cylinder, okay, or plane, etc. In these cases, it is actually very much uh, easier to calculate the electric field due to that charge distribution, whether spherical, cylindrical, or linear or planar charge distribution. Okay. Now, before we go to the details of Gauss's law, let me just tell you about uh, a related term, electric flask. So we have already learned maybe about flask, water flask, etc. Suppose I have a plane like this. Okay. So what is electric flux? It is the actually it is the number of field lines field lines number of field lines passing through any surface perpendicular to so it is the number of field lines, electric field lines passing through any surface perpendicular to the direction of. So surface has to be perpendicular to the direction of the electric field lines or the electric field. This is so if suppose this is a perpendicular plane, or let me just redraw once again. Okay, so this is kind of a vertical plane, and see, electric flask is actually, suppose I have electric field lines passing through, this is 3. So if I have 10 area of cross section, so I can say that the flux line, 3 flux line is passing through the surface which is perpendicular to the direction, in the direction of the flux. Okay, so this is number of flux. So flux has unit Weber, WB. This is Weber. Now, electric flux, as I said, it is the perpendicular, it is the number of field lines. Flux is number of field lines passing through a surface across it, like passing through it, and the surface through which it is passing should be in a perpendicular perpendicular to the direction of the field. So the area has to be perpendicular to the direction of the field. Now look mathematically how we can express that field. As if flux is generally denoted by pi, so generally electric field flux is equal to E into A. E, so electric field A is the area. So here area is the ds, so I can just write in general, say E dot ds. E dot ds close, so this is path integral, surface integral. So E ds, that has to be actually calculated first. So this is actually, so flask is this one. If you want to calculate the total flask, so now this could be written even E ds cos of theta. So what is the ds and what is E? E is the electric field, as you know. So the flux is phi integration size E dot ds. E dot ds is E ds and cos theta. This way we can write. So what is the cos theta? Cos theta is the angle between the ds. Ds is the area vector and E is the electric field, direction of electric field. So area is, how is it possible that I can get area vector? Yes, area is vector. So its magnitude is this area vector. It will have a value ds, but what is the normal? Okay, so ds is okay. All right, so how do you find out this ds, direction of ds? So this is the angle between this. So you know how to take the direction of an area. So if the area is closed surface, okay, so closed one, then so then the direction of the area has to be taken. So normal has to be taken outward normal in case of closed surface. All right, so outward normal. So this will be outward normal, but if it is open surface, then I can take, like my screen, I can take normal in this way also. Okay, so I need this figure alone. So in this case, we can see that DE, I'm sorry, this DS, so DS is area vector actually. DS is area vector. So area vector, if my surface is, this surface is open surface, so I can take area vector will be having magnitude and direction will be always outward normal in case of closed surface, but in case of open surface, any direction which is perpendicular to this. Okay, so DS, suppose I can take just an open surface like this. So I can take the normal or area vector in this direction also or in this direction also. But we should remember that when we rotate the area, they should not change. So that will be the criteria. So these are outward normal taken when the open surface, the surface is open. But when I am having a closed surface, balloon, so in case of closed surface, the normal has to be always outward normal. So outward normal in case of closed surface, but in case of open surface, I can take the ds vector or area vector in either either direction of the surface. Okay, now look, when the flask, so flask we have seen flask is equal to eds, let us say e dot ds in vector term itself. So what is the phi, sorry, what is the flask? If this electric field is this, and suppose electric field in this case actually it is maximum. Okay, in this case it is maximum because see this direction of electric field is so we know ed cos theta or ds cos theta. So what I'm trying to say is that see in this case electric flux and the area normal. So anyway, this is perpendicular to the surface. So we have finite electric dipole. Sorry, field due to dipole. Okay, sorry. This is actually flask. What I'm trying to say is this, and see, this is non-zero flask. Okay, this is non-zero flask. But when the field, electric field is tangential to the surface, as you see, in that case, the direction of the area vector and electric field will be perpendicular to each other. So cos 90 is 0. So this will be, flux will be 0. Suppose I have a surface like this. If the electric field lines are going like this, so what is the flux through it? That is 0. Flux is 0. Through this is 0. So this is what I am trying to show here in this two figure. So this is what it is. A in case we are calculating electric flux using Gauss's law, so in that case, see, Gauss's law will be this: E dot ds, and right hand side q by 4 pi epsilon naught. So this is actually Gauss's law, 1 by q by epsilon naught. So in this case, the left hand side always electric field through the surface must be constant. This must be always directed towards the, like, at the perpendicular to the area vector. Okay, so this is the case. So so in this case, you look, this is, see, everywhere the normal to it is actually 90, making 90 degree. Okay, that means electric field is actually perpendicular to the surface, whatever we are considering the charge distribution to be. So electric field, value of the electric field at any point has to be constant. That should not vary. Then only Gauss's law will be applicable for a particular symmetry. Okay. So application part of Gauss's law, if we see, as I said, see, this is the Gauss's law, q by epsilon naught. So this is actually in case of free space. Okay, so to apply this formula for, suppose, for a point charge, we want to calculate for a point charge. So electric field, applying Gauss's law, we are calculating electric field for a point charge. So how to do that? In this case, suppose this is the point charge, we have to first construct a Gaussian surface. And see, the electric field lines are actually going perpendicular to. Okay, so the field lines are like this. Now you have to actually consider a sphere of radius r. Okay, so Gaussian surface at a distance r. So this point, see, electric field will be always constant on this surface. So this will be out. Now we have an integration this. So this integration for a spherical surface will be 4 pi r square. And on the other side, the q by epsilon 0, right? Q by 4 pi r square, q by epsilon naught. Now E is equal to q by 4 pi epsilon naught r. This is not r square. I'm sorry. This is r square actually. Okay. So this is, see, how we get electric field due to a point charge. Okay. So this is actually electric field due to a point charge. So I have to first construct a Gaussian surface, and, according to the, or suitable for the distribution of charges. For point charges, we will take spherical symmetry. For line charges, we have to take cylindrical symmetry. For planar charges you have to take plane. Okay, so this is how we have to do. So in the next class we will take various applications of Gauss's law. I think we will stop it here for today. So thank you for your patience. Bye for today.